minute late. Something like that. I might go overtime in here sometimes. Preston's like, uh-oh, he said he's doing it. That's bad. It's true, yeah. All right. So some of you hadn't had my classes before, so let me just talk a little bit about how things work in here. So this is my webpage, and if you scroll down here a bit, there is my current schedule. I'm teaching 5 classes, and then there's a 6th one, but it doesn't count. It's online. But I have office hours 9:10 to 10:30, Monday, Wednesday, Friday, and then also 2 to 12 to noon. 12 to noon, sounds wrong. Noon to 2, Monday, Wednesday, Friday as well. That's the current plan. I'm still waiting for Preston and Dr. Sprano and whoever else is involved in that to decide when Galois theory is happening.
It's my choice, actually.
It's your choice?
My choice.
Oh, interesting.
So I'll let you know.
All right. It's always a dangerous thing scheduling some kind of class like that. Like I once co-taught a course in topology with Dr. Skambordis. And he decided that we'd do it at 7 in the morning. It was a spring semester. There was a day or two we got here, and then he was like, oh yeah, I'm not teaching today. I was like, so, but it was fun. It was fun. Served its purpose. All right. So anyway, these are my schedule, and then if you go back up here, I have links to course web pages. There's more stuff down past this part. You can see my research and junk if you go down there, but who cares? Here we're in advanced calculus. Is this course website not updated for 2025 yet? That's a lie. It is updated, and so if you look here, there is this YouTube playlist. This is where I will post the lectures for this class. Obviously, there's nothing there yet since we haven't had a lecture yet. And course plan, I just gave you guys a copy. Here's the one with color. There you go. You don't even like paper. What are you complaining about? So, where's your copy? Why didn't you get one when I handed it out?
I was just out of the room.
How dare you? I guess you can have this one. So I don't follow a book in here to start with, except that I follow this, which is, I've been accused of this being a book. I don't know. It has 264 pages. I guess that's enough. But so basically, this is what we're following for a while. Eventually, I will start supplementing here and there bits and pieces with the required textbook, which is Paul Retland's text. So we'll get to that eventually. But I'll probably always be poking around with some stuff in these notes, even to the end of the course. But all right, so there's that. So you should definitely be looking at this as you study this course. All right, like don't ignore these. Every so often, I have a student who's in my class and somehow doesn't hear me say I have lecture notes and ignores them, and they're very confused about 3 weeks into it. Yeah.
That's me.
That was you. This was not intentionally a story about you, but I like that it worked that way. Yeah, and then so the missions are the required homework. So like here's mission 1. It's got problems. You do those problems. There's a bonus problem. I forget how did I award you? I gave you points for stuff. Let me see what that was. Points. So there's 2 tests and a final. Test 1 is 250. Test 2 is 250. Missions are 250. But technically you could earn 270 points if you did everything in there, not including the bonus. The bonus are worth, there's another 50 points bonus you could earn doing the bonus problems. Some of those are not easy. So don't think I'm as generous. It's not as generous as it looks. It's not. So we'll cover a lot of different things, I hope. So today I'll talk about vector spaces and norms and so forth, bits of topology and vector spaces. Next time we'll do limits, hopefully. And then like next week we start into derivatives and differentiation and so forth. And basically, essentially all we're doing till test 1 is calculus over a vector space. That's pretty much all we're doing. If you don't know what a vector space is, don't worry, we're going to talk about it soon. And then past test 1, we do more interesting things, a variety of things involving differential forms, a little bit of this and that and the other thing. I think the topics after test 1 are much, in some sense, more interesting. And I will get more sketchy after test 1. All right, so, but anyway, that's kind of the course in a nutshell. That's what we're going to do. Any questions? Yeah.
What do you mean by you'll get more sketchy?
I won't prove everything. Let me restate that. I will prove less things. Yeah.
I'd like if you could prove everything.
If I could prove everything, well, how much time do you got? So, all right. With that said, let's get to it. Put this away here. I will eventually top hat in here, but let it be understood, I don't care about that. Your real attendance is here. This is how I judge your attendance. So if you miss a top hat code someday, it doesn't matter, because this is where I count attendance from. I am required to top hat every day, apparently, and so I'll try to do that. But anyway, all right, so let's get into it. What is a vector space? So first of all, has anyone here not had 221? Okay, so you've also not had 321. Correct. All right. So this will be a little bit more challenging for you guys, but let me just kind of give you a quick answer for what is a vector space. It's really nothing to be scared of. A vector space is simply an abstract set in which you can add things and multiply by numbers. That's it. That is what a vector space is.
What's the name of the class for 321?
Linear algebra.
Okay.
Yeah.
I think it's differential equations. I've done fingers.
Oh, so that'll help. But I wouldn't let that scare you off. But you'll learn more than some other students. So let's talk a little bit about linear algebra. So I'm not even going to define it formally in here. I'm just going to tell you that a vector space is a set which allows for addition and scalar multiplication. And so I'm going to give you some examples. So the first example is Rn. So this is the set of n tuples. So of course the coefficients are real numbers, right? And how do we define addition in here? If x and y are in Rn, then x plus y, the ith component of it, and a constant times x, the ith component of it, how do we define those? Well, the way we do that is we just add components, right? So the ith component of x plus y is x sub I plus y sub I. The ith component of cx is just c times x sub I. So these right here define addition and scalar multiplication in Rn, right? And this matches your tip-to-tail vector addition you guys have seen in Calc 3 or whatever. But it's also totally n-dimensional, right? So I can't draw pictures, but I can do the algebra. One other just brief point of notation here is that this right here, guys, in my class is a shorthand for a column vector. So that's actually a notation for this, right? In contrast, if I was to write this would be something else. This would be an element of what I would call R 1 by n. So that actually brings me to my next thing, which is matrices. All right, so Rm by n is equal to, A such that, A is m by n matrix with Aij in the reals. So let's talk about matrix notation for a bit here. So if A is an element of our m by n, then we can write A a few different ways. So one thing we can do is we can write A as like a bunch of columns put one after the other. So we've got like column 1 of A, column 2 of A, and so forth and so on. Eventually you get to the last column. How many there are? Well, this is m by n, right? M is in mommy, n is in nenu nenu. Sorry, I know I needed a better reference. Like, I was talking to the last class. Like, I know Mork and Mindy is long since forgotten. It was a dead show when I was little. It's even more dead now. I'm still talking about it. I don't know why. Certainly my parents didn't really like it. I think my mom hated it. I just like to sing nenu nenu. Anyway, so there are n columns here, so n. So that's one thing. We can look at it as columns one after the other. These vertical bars are just, notation for putting things together. Concatenation, as it's called. You can glue the columns together to make the matrix if you like. Of course, we can also look at it as a stack of row vectors, like row 1 of A, row 2 of A, row, how many are there? There are m of them, m as in mommy. So a stack of row vectors or, concatenation of column vectors. Okay, so let me just say here, like the formula for this. What is if I take the ith row of A and I calculate the jth component of that, what's that equal to? What if I take the jth column of A and I calculate the ith component of that, what's that equal to? Wow, this is flat. Ah, it's so flat. I got to save some. So, Aij, right? Actually, both of these are Aij. Right. So I is the row index, and j is the column index. So if we fix I and we let j vary, we're looking at a row. If we fix j and let I vary, we're looking at a column, components of the column. All right, what's the definition so this is a vector space, all right? Or you can also call it a linear space. A linear space is another name for vector spaces, which is kind of a better name for it because it really describes what a vector space is, which is a space which allows for linear combinations to be in the space again, right? So like the definition of matrix addition and the definition of scalar multiplication is pretty much the same we just wrote, right? You just do it component-wise. And if we were to state the definitions of a vector space formally, there's like 8 or 10 axioms depending on how you count. You could go down the list and check that these definitions for scalar multiplication and matrix addition satisfy those axioms for a vector space. It is in fact a vector space. All right. But it's more than that because there's something else we can do with matrices, which you probably recall, which is what? What else can we do? Besides adding matrices of the same size, what can we do? If we've got A in R m by n, and if we've got B in R n by p, then A times B, does that make sense? I think it does, is an element of what? R m by p, and how is it defined? A couple different ways to look at it, but AB, the ijth component of it, one way we could look at it is formed from taking the ith row of A and taking the dot product with the jth column of B. I'm assuming you can make sense of what I mean by a dot product of a row and a column, right? Technically speaking, from a math student perspective, there's something a little bit sketchy about that because I'm taking the dot product of disparate objects, right? I'm taking the dot product of a row vector and a column vector. That makes sense because they've got the same size, right? But you've been taught a certain legalism in your mathematics. It may offend that if you think about it. But it is nevertheless a reasonable thing to write. And that is this isn't, if you read, higher math, this kind of thing is done. Really what that's doing is making use of an isomorphism between objects is what's going on. And it's just no one's interested in writing down the isomorphism. But anyway, here's more to the point. Here's a formula. The sum, k equals 1 to, what do we got? N of A, I, K, B, K, J. So there you go. That's my preferred definition for matrix multiplication right there. All right. So that's number 2, our second example. My third example is Cn, complex n vectors. Cn, you've got like z1, z2, zn, such that z sub I is in the complex numbers, right? And example 4 is Cm by n, which is going to be, matrices of the form like this, where Aij is in the complex numbers, and 1 is less than or equal to I is less than or equal to m, and 1 is less than or equal to j is less than or equal to n. In other words, m by n arrays of complex numbers are m by n complex matrices. Now the definition for how we add and scalar multiply complex vectors or complex matrices, it's just the same as I did in examples 1 and 2. I won't even write it out, all right? You just add component-wise, okay? Now, all right. Another example, and this one's kind of a little bit heady, but if we have V and W are vector spaces over the reals, let's say, then HOM R V comma W, which is going to be like L mapping from V to W such that L is linear transformation. So this is for homomorphisms. If we have, this is another thing we'll define, end R of V would be Homer VV. This is linear transformations on V. For those of you who have not had linear algebra yet, do not fret. I don't think we use this too much, but anyway, so this is again a vector space because it turns out if you add two linear transformations together, you get another linear transformation, and you can also scalar multiply a linear transformation and get a linear transformation. It's also interesting sometimes to look at a subset of these, which are the invertible linear maps. Yeah.
Is that your shorthand right for the home set theorem, or is that?
Then. Yeah, no theorems yet.
Okay.
Don't worry. Eventually I'll actually say something. Every question that was asked in Math 200 today, the answer was, that's the definition. Like, why is implication like it is? That's the definition. Why does false imply true? Why is, if false implies true, why is that true? Because I said so.
Curly bracket.
What's that?
Did you close your parentheses in the curly bracket?
Because I wanted to.
That's the definition.
Okay, so anyway, so I'm not sure 5 is even necessary. I kind of regret putting this here. I feel like it's distracting us, but anyway, here, this is GLV. So here you're looking at L in the endomorphisms such that L inverse exists. So these would be the invertible endomorphisms. Not every endomorphism is invertible. For example, you've got like the zero map is a linear transformation which is not invertible, right? For those of you who've had linear algebra, you remember if the kernel is non-trivial, that means it's not injective, so it can't be invertible. For the rest of you, that doesn't matter for this course. Okay, so I don't think. Definition. Question? No? No. If V is real vector space, and S is a subset of V, then define the span of S as follows. Span of S is equal to C1 S1 plus plus CK SK such that S1 and all the way out to SK are in S, and C1 through CK are in the reals, and K is a natural number. All right. Let me put this into words. The span of a set is simply the set of all finite linear combinations. So this is the set of all finite linear combinations. All right. Taken from S. Now, in the case S is a finite set, you can just take the linear combinations always to be as big as the set is, right? So if I had like linear combinations of 3 things, I would just do like C1 times the first thing, plus C2 times the second thing, plus C3 times the third thing, and that would be the span. But this definition allows for the possibility that S is an infinite set. So even if S is an infinite set, in regular linear algebra, we just take finite linear combinations. There are places in analysis where you extend the notion to like infinite series of things, but that's another matter. So a span is a set of finite linear combinations. Oh, here's a theorem for you. Theorem. Span of S is a subspace of V, given S is a subset of V. Let me explain the notation. What is a subspace of a vector space? What's a subspace of a vector space? Yeah.
It's a closed vector space within that vector space.
It's a closed vector space within that vector space. That's a good way. Yeah, it's a subset of the vector space, which is again itself a vector space. And also with respect to the natural notions of addition and scalar multiplication, it inherits from its like parental set. Right? So we can't make up some newfangled definition of vector addition on the subset and say it's a subspace, right? Like there are ways, for example, if you have a plane in Euclidean space like R3, you can define vector addition of vectors on a plane in R3 to make it into a 2-dimensional vector space. I don't know what dimension is. We'll talk about that in a second. But you could define an addition of vectors on a plane which doesn't go through the origin, which would make that into a vector space, a 2-dimensional vector space. Yet that would not be a subspace of R3 because it doesn't contain 0. The reason what's going on in that situation I'm talking about is that the definition of vector addition on that plane would not be the standard definition. It would be a modified one based on the particulars of the plane. So it's a subset which is itself a vector space with respect to the natural notions of addition there. I don't know why I'm being so careful about this. We don't talk about subspaces much in here. What's wrong with me? Let me go on. So Brevity's the soul of wit, so you figure it out. So S is if so some more terminology. If the span of S is equal to V, then S is a generating set or spanning set, if you like, for V. All right? I guess that's a definition. Everything's definitions today. I'm sorry. So that's one thing. Now, there's another very important idea for vector spaces, maybe only second. I don't know which one's more important, spanning or this one. Will you guys decide? Definition. So let S be a subset of V, a real vector space. Then S is linearly independent, which I'm just going to abbreviate as Li. Linearly independent, if and only if C1 S1 plus, let's see here, my bad. If and only if S1 through SK in S and C1 through CK in R with C1 S1 plus C2 S2 CK SK equals to 0 implies C1 equals to 0 all the way out to CK equals to 0 for K in the natural numbers. Okay, so again, I've given a definition here which is going to work for an infinite set. All right? An infinite set is said to be linearly independent if any finite linear combination taken from the set, put equal to 0, is necessarily the trivial combination. Right? So this right here, guys, is a linear combination. And, you know, there is an easier way to write this, isn't there? Can you guys tell me? Yeah, I could use a summation notation, right? I could also write this as like the sum I equals 1 to K of Ci Si equals to 0, right? That's a linear combination, a weighted addition of terms where the weights are taken from the field in question. So this is a linearly independent set. So definition. So a spanning set gets you the whole vector space, right? But the trouble with an arbitrary spanning set is you might have more vectors than you need, right? So if we're trying to like describe how to build a vector space with a certain like fundamental building blocks, if you will, we want a spanning set, but we also don't want to have more than we need. And so if we have a spanning set which is also linearly independent, that gives us what's called a basis. And with a basis, if you pick any vector in the vector space, there is a unique way to build that vector from a basis. That's why we're interested in basis. It gives us a unique way to build vectors with respect to a given basis. So let me define that. If V is equal to the span of beta and beta is linearly independent, then beta is a basis for V. All right. The cardinality, the number of things in beta, is equal to the dimension of V. So if you have an infinite basis, it's said to be an infinite dimensional vector space. If you have a finite basis, it's a finite dimensional vector space. One of the things we prove in 321 is that the basis is well defined for a vector space. If you have a vector space, you have two bases for a vector space, they have to have the same cardinality. Now, you guys don't know what cardinality is? I'm just talking gibberish, right? Cardinality is just the size of a set. So like, you already know cardinality of things. Like if I have three things, the cardinality is 3. It's just counting for finite. For infinite things, that gets more interesting. Like the cardinality of the natural numbers is called aleph naught. The cardinality of the real numbers is called aleph 1. The continuum hypothesis states that aleph 1, there's nothing between aleph naught and aleph 1. The next infinity past aleph naught is aleph 1. And then there's the whole tower of infinities past that. If you want to know more about that, don't ask me. Ask Dr. Sprano. His thesis is in this stuff. Transfinite arithmetic and such. But okay, so basis. Now, so almost, well, I can't say exclusively, but a lot of the times we're just interested in a finite dimensional vector space, all right? So let's focus our attention there. So definition, if beta is V1, V2, Vn, all right, then x1, V1, my bad. Oh, I'm stating a theorem. Sorry, guys. Let me get through the rats. I mean, they should swap that definition out for a theorem, if you don't mind. Theorem. Okay. Let beta be if this is a basis, right, for V, and x and y are vectors in V, then x1 v1 plus da 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 plus xn vn equals to y1 v1 plus yn vn implies what? Yeah, implies x equals y. So this implies I've worked myself into a corner. Give me a second. Yeah, I'm sorry. This theorem's not interesting yet. Give me a second here. Forget about the x and y and v for a second, okay? There exists, x1, xn, y1, yn in the reals, such that this. What's that imply? So if that's a basis, that means it's linearly independent. One of the big things about linearly independent sets is we can equate coefficients of linearly independent vectors. So like if this is linear combination, if that's a basis, that means that whatever is next to V1 on both sides, it has to be equal, right? And whatever's here has to be the same as there. So the implication here is, the conclusion is then x sub I is equal to y sub I for all I n. All right. So you can equate coefficients of a basis. We use this in Calc 2, if you think back to it. Like in Calculus 2, you guys remember like partial fractions? For instance, in partial fractions, we'll have like a sum of things and then we equate like terms. If you really look back at those calculations, you'll see that what you're using is linear independence of the functions that you're building the fraction from. All right. Sorry if I'm going kind of fast. It's because this is not really the part we need to belabor. We really just need terminology here. You do need to know the definition of span and linear independence. That matters. I'm going to ask you questions about spanning and linear independence. So it's good to know what you're after there when that happens. Okay, so definition, if X is in V with basis beta equal to V1, V2, Vn, and X is equal to X1, V1 plus, Xn, Vn, or if you like, we could write it this way, the sum I equals 1 to n of X sub I Vi, then define the coordinate vector of X with respect to beta as equal to the column vector X1 through Xn. Another way to think of this is we're defining phi sub beta of X equals to this. So here, phi beta is a mapping that goes from the vector space to Rn in the current context. We're only going to look at real vector spaces in here, all right? So a vector space is a real vector space. I keep it real. Even my complex examples, we're going to look at those as real vector spaces, all right? I'll show you. So this is the coordinate map, right? So the obvious next question is, what are the bases for my examples? Is there a basis? Can we write down a basis for examples? So like, some of this is really dumb. Like example 1, for 1, Rn is the span of E1 out through En. For 2, Rm by n is the span of, let's say, Eij, such that 1 less than or equal to I less than or equal to j. Excuse me, 1 less than or equal to I less than or equal to m, 1 less than or equal to j less than or equal to n. Excuse me. Now, of course, this begs the question, what do I mean by these symbols, right? What do I mean by EI and big EIJ? What are those things? You guys know? Some of you know, some of you don't. Let's pin it down. So here, let me find a different color. So here, EI, this is the so-called standard basis. EI, if you calculate the jth component of that, it's Kronecker delta Ij. So this funny looking symbol here, it's 1 if I is equal to j, it's 0 if I is not equal to j. This is the so-called Kronecker delta. Kronecker delta. That's just a fancy way of saying that these are the vectors which have a 1 in the ith spot and 0 everywhere else. In the same fashion, we can define these guys, the so-called matrix units, Eij, the kth component of that is Kronecker delta Ik, Kronecker delta Jl. This is the so-called matrix unit. And it's not a unit in the sense of like abstract algebra. I mean, it's not an invertible matrix. It's a matrix which is almost all 0. It simply has a 1 in the ijth spot. So, question, this coordinate vector that I said in words, I probably should tell you here, this is the coordinate vector of X with respect to beta. Is that unique? I mean, it had better be. I told you it's kind of what I was trying to get to in my previous mumblings is that it gives you a unique description of each vector in the vector space, right? The coordinate vector uniquely corresponds to the vector, all right? In the same way that like coordinates in Cartesian, like, coordinates, like the Cartesian coordinates of a point correspond uniquely to the point, right? Same idea here. So the issue that I haven't quite addressed yet is important that, and I should really say this is part of the basis concept, is that it's an ordered set. We need this to be an ordered set. Right? Otherwise, since vector addition commutes, I could switch around the orders of the terms and I get different, coordinates. So it's an ordered set. So that starts to get a little bit fuzzy here, because how do you order? I mean, okay, this is clear enough. Like, this order is natural, right? Only a weirdo is going to do like en minus 1, e2, e1, right? You're not going to do that. I wouldn't do that. But how about these? Like, let's be more specific. How about like 2 by 2? I'm telling you that's the span of Eij. But that doesn't quite pin it down in terms of the basis. So here's our convention. We'll do it like this. We'll do E11, E12, E21, E22. This is the so-called lexicographic ordering. So the idea of it being, it's kind of like alphabetical ordering, where the first letter takes precedence, right? The first index takes precedence. So you list out all of the matrix units which have a 1 in them in order. That's the start. Then you go on to the ones with 2. And well, that's it for here. But yeah. Let me be like way more specific. So like, here's an example, just to bring it back down to earth for a second here. Wait, this is our first example? This might be our first example. This is special. All right, so let me make it weird. A, B, C, D. All right. This is a 2 by 2 matrix. I'm just letting it be arbitrary for the sake of, adding confusion. But this is A times 1, 0, 0, 0 plus B times 0, 1, 0, 0 plus C times 0, 0, 1, 0 plus D times, just barely made it, 0, 0, 0, 1, right? So this guy right here is E11, this is my E12, E21, E22. So see, I have written them in the lexicographic ordering. What is the coordinate then? What's the coordinate vector of this matrix? What's phi beta of A equal to? Sorry, Kronecker delta, you got to go. I'll write it as a column. Yep. Well, that wasn't very exciting, but yes. Thank you. Exactly, A, B, C, D. Do you guys understand? I mean, this particular example you understand, but that's the basis. Now, there's a little bit more to say about the complex examples, but I think I'm going to go on because it's actually, we'll come back to those when we need it in homework or whatever, but basically for the complex examples, you have to use the standard basis and I times the standard basis for a basis. And there are kind of like two different natural choices for how you order the bases. One gives a nice formula in one sense, the other gives a nice formula in another sense. So they both kind of have their place, but I'm going to move on. Let's talk about what is a norm. Tell you what, rather than me writing out the general definition, let me illustrate what I'm talking about in the complex case with an example. That probably would be more useful to you guys. Well, there's two kinds of students here. There's students who are going to read my examples, my definitions for the complex stuff, and you're just going to be like, yawn. And then there's those of you who have not had 221 yet, and you're going to read the complex examples, and it's going to be like, what is this? So for the sake of you, and everybody else actually, let me just give an example rather than giving the full definitions for the complex thing. So like, all right. So example 2, we'll look at 1 plus I, 2 minus 3I, 4, and 6 plus 7I in C4. All right, what's that? I'm not sure what Preston's up to, but I'm going to ignore him. So E1, IE1, E2, IE2, E3, IE3, E4, IE4. That is a basis. That's a basis for C4. So what I'm saying here is, let me give this thing a name. Let's call it, we'll call it Pac-Man. So if you look at this, Pac-Man is equal to 1 times E1 plus 1 times IE1 plus 2 times E2 minus 3 times IE2 plus, I actually done 3 dimensions. What's wrong with me? 4 times E3 plus 0 times IE3 plus 6 times E4 plus 7 times IE4. The rules here, guys, is we're dealing with a real vector space. We're only allowed to use real coefficients in the span. So the i's have to get sucked into the basis is the idea. But if that's the case, then the coordinate vector of Pac-Man, what is it? Mm-hmm. Mm-hmm. 2 minus 3. Yep. 6, 7. So that's one path we can go down. The other kind of basis we could make, though, can you guys think what would be the other kind of natural ordering for these as a basis for C4? We could say gamma. How about this? What if we just did E1, E2, E3, E4, and then what? By the way, these are just 2 choices. For a vector space, there is always infinitely many choices of a basis. Because every invertible matrix you guys learned about in differential equations, did you also have differential equations? Okay, every invertible matrix you guys saw in differential equations can be used to take a basis that you're given and come up with a totally new one. How many invertible matrices are there? Infinitely many. So there are always infinitely many choices for a basis on a vector space, as long as we're working over a field of characteristic 0. But let's see here, IE1, IE2, IE3, let me try to keep it continuous in here, IE4. That is another, and that one in some sense is way easier, because if you look at Pac-Man, you can write Pac-Man as 1, 2, 4, 6 plus I times, 1 minus 3, 0, 7. And this would be the real part of Pac-Man. And this would be the imaginary part of Pac-Man in this context. And so the gamma coordinates of Pac-Man are simply like real part of Pac-Man, comma, imaginary part of Pac-Man. This is actually a general truth. If you go back and look at what this formula is doing, what this is doing here is like real part of Pac-Man 1, imaginary part of Pac-Man 1, real part of Pac-Man 2, imaginary part of Pac-Man 2, and so forth until you finally get to the real part of the fourth component in Pac-Man, and then the imaginary part of the fourth component in Pac-Man. So each of these choice of bases has their place in the context of like complex 4 space, but you can see why each formula would be nice. All right, I think I spent too much time on that. At this point, I have to get the projector out. I'm sorry. So, oh yeah. All right, so come on. Well, I will find it. There we go. Beep, 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 beep. We made it this far. All right, so. Oh, you double scrolling, you. I hate you double scrolling. Stupid double scrolling. All right, come on. So here is, what I was just saying for n column, for n dimensional complex vectors, we can either, if we've got z is x plus iy, then like the one choice of coordinate would be just x comma y. And the other one, we're just stringing out the real and imaginary parts of each of the components. Those are kind of the two natural choices for coordinate maps on CN. And the same thing goes for complex matrices. So an n complex vector is actually 2n real dimensional. This starts with the complex numbers. The complex numbers correspond to the plane, right? The plane is 2-dimensional, even though it corresponds to just one complex dimension. So there's always like a dimension doubling when you go from complex to real. All right, so next up, we should talk about normed linear space. So let me write that down over here. Actually, let me not write that down because, sorry, I may be lazy. So what is a normed linear space? If you have a vector space and you also have a definition of like the length of a vector, we call that the norm. What are the properties that the length of a vector has to satisfy? It has to satisfy, if you've got a scalar multiplication, you can pull out the absolute value of the scalar, right? So like that's a property of vector length if you think about it. If I multiply a vector by -2, the length of that vector is twice the length of the original vector. This has got to be true for a norm. It has to satisfy the triangle inequality. So the norm of a sum is less or equal to the sum of the norms. The length of a vector has to be non-negative. So you can't have like a vector length of -1. This is not allowed, all right, by definition. And also, the only way that the norm can be 0 is if it is actually the 0 vector. So if we have a vector space paired with a norm, it's called a normed linear space. Or if you like, and I certainly like NLS, right? It's like, saves us so much writing. Like LI is one of the best abbreviations ever, you know? There's certain things in math missing abbreviations, but anyway. Here's a fun one. In Math 200, I accidentally gave them a proposition that is labeled T, capital T. That wasn't on purpose, but, and I think the question is about truth tables. probably should go fix that. It's only going to cause chaos. Maybe I'll just leave it, I don't know. Okay, so so obviously the next question is, what are the norms on our examples, our example vector space, right? So on Rn, the Euclidean norm is defined by the square root of the dot product of the vector with itself. This is just a fancy, let me write that out over here for you guys. So like, what is the norm of V? I say it's the square root of V dot V. What's that mean? V1 squared plus V2 squared, right? This should be familiar to you, right? This is just the standard Euclidean norm, as it's called, for Rn. Just to unwrap that notation for a second. So that's the Euclidean norm. Now, the interesting thing is there is more than one choice of norm for Rn. There's also something called the taxicab norm. The taxicab norm is defined to be, like here, it's the sum of the absolute values of the coefficients. So like the one norm of V is the sum of the absolute values of the components. So for example, if I was to say, what's the taxicab norm of 1, 2, 3? It would be 1 plus 2 plus 3, right? Now that's of course different than the Euclidean norm. The Euclidean norm of 1, 2, 3 would be the square root of 1 squared plus 2 squared plus 3 squared, which is what? 14, square root of 14, right? Is square root of 14 equal to 6? No, so these are different notions of distance, right? I say distance, the norm naturally calculates the length of the vector, which we could think of as the distance from the origin out to where the vector points, right? So there's also something called the sup norm. The sup norm on Rn is defined by, you take the maximum of the absolute values of the coefficients. So like if I calculate, let me keep my list down here. So the Euclidean norm was square root of 14. We calculated that. What's the sup norm, or what, or what's sup? What's it? So the sup norm is 3. It's just 3, right? Because the maximum absolute value of a component there is 3. It's kind of a weird way to calculate the length of a vector, isn't it? It's kind of the calculus of if you get cornered in an alley by a gang of thugs, whatever thug defines the length of the sup norm is the one you should attack, right? Because you have to show the others that they're weak, and they won't, it's just like the old. And you have to go, well, anyway, I stopped.
Well, what if you consider the subnormal all four of you, and you're not?
There,
Subnormal.
if there's thug symmetry, so they're all the same.
No, you're not strong.
Oh, if you're not the strongest, then it's just you're done. Yeah.
So all this definition and all this other stuff that you did before, you opened the projector is only defined for the Euclidean norm, or am I asking the wrong question?
I'm not sure yet. Hang with me here for a second. So what I'm showing you right now, these are 4 different competing notions for norm of an n-dimensional vector. After we get done with this discussion, we're going to agree almost always to use the Euclidean norm to calculate the length of a vector. But it's important to know that there are other choices. Partly because there are arguments, there are some arguments which get way, way easier if we use the taxicab norm, it turns out. And well, let me hang with me here. You'll see why we're talking about it in just a minute. But there's also something called a p norm, where you take the sum of the p powers of the absolute value. You take the 1 over p root of this. So like p equals to 2 is the Euclidean norm, p equals to 1 is the taxicab norm. And if you think about p going to infinity, it gives you the sup norm. And so I think it's interesting in each